Welcome to the Chapter 10 review problems. Hopefully what you've done already before you're watching this video is you've actually practiced these problems on your own to see if you can do them. Now you're just here to actually see if you've done the problems correctly. So if you haven't done the problems yet, you should probably wait on the video, do them first, and then go ahead and watch the video and check your answers. Alright, so here we go. On the first one, how many moles are there in 0.028 grams of iron? So we're in grams of iron and we want to find moles. Highly encourage you to analyze that problem. So circle what you're looking for, underline what you've been given, and that underlined point is your starting point. So you're in grams of iron and you want to convert into moles. So we're going to use the molar mass. Anytime we do molar mass, it's 1 mole that we're going to put into our fraction, and we just have to decide where we want to put that mole. Well, because grams is up here on the top, I'm going to have to put grams of iron down here. So that means that 1 mole of iron is going to go up on the top. So now we look for that molar mass of iron from the periodic table, which is 55.85 grams. The grams of iron cancels out. We're left with moles of iron for our units, which is what we were looking for. And then just let your calculator do the rest of the work for you. So it comes out to be, and we kind of need it in scientific notation because I need 2 sig figs here. So it's going to be 5.0 times 10 to the negative 4th moles. Final answer, circle it. Okay, the next one, how many particles are there in 0.5 moles of the silver chloride? So again, analyze the problem. We're looking for how many particles. We've been given the 0.5 moles. And that is going to be our starting point. 3 sig figs. Remember to pay attention to that. So our starting point has 3. We need 3 in our final answer. And that is in moles of AgCl. And so in this one now, because I'm talking particles, then I'm looking at Avogadro's number. So 1 mole is what I'm going to use in my fraction. I'm going to put it on the bottom this time. And Avogadro's number says there are 6.02 times 10 to the 23rd particles in 1 mole. Now the only other thing you have to decide is what kind of particle. So we're looking at a metal combined with a non-metal, that's ionic. And ionic, we use the formula unit. So it's formula units of AgCl. The moles of silver cancel out, silver chloride. And let my calculator do the rest for me. And making sure my final answer has 3 sig figs. So it's 3.01 times 10 to the 23rd formula units of NaCl. Question 3, again another particles one. So circling that, that's what I'm looking for. But in this case, I'm starting off in the grams. So this is one of those 2-step problems. So I got 1.00 grams, 1.00 times 10 to the 4th grams of the mercury. Got to get out of grams, so I'm going to use that molar mass to begin with. And in 1 mole of the mercury, I have 200.59 grams right off the periodic table. Now I'm out of grams and I'm in moles, but that's not my final step. I want to get into those particles. So I'm going to use Avogadro's number. 1 mole going on the bottom, so I can cancel it out. And the 6.02 times 10 to the 23rd. And this time I'm dealing with a single element mercury, so the particle units are going to be atoms. Okay, calculator does the rest of the work for me. Multiply all the tops, divide by that bottom, and with 3 significant figures, it's going to be 3.00 times 10 to the 25th atoms of mercury. And there we go. On to question 4. How many grams are there in this many molecules? So we're basically doing the same thing but in the opposite direction. Now I'm trying to find how many grams and I'm in particles. So starting point is that 1.20 with 3 significant figures that I'll have in my final answer. And my first step then is going to be Avogadro's because I got to get out of the particles and into moles. So 1 mole of the Br2 up on top. The 6.02 times 10 to the 23rd this time is going to go on the bottom. And that's molecules of Br2. And then my final step is going to get from the moles that I'm currently in, because that would cancel out the molecules here. So putting 1 mole on the bottom, and then I need that molar mass for that on the top part. Now, because it's a molecule and it's 2 bromine atoms, I need to multiply the molar mass by 2. So it actually is going to be 159.8 grams of the Br2. Moles cancels out. Take that number times 159.8 divided by Avogadro's number, and with 3 significant figures it works out to 3.19 grams of Br2. Number 5, which one has more atoms, 6 moles of carbon or 6 moles of lead? Well, 1 mole of anything, when we're talking about the number of atoms or the number of particles, Avogadro's number says 6.02 times 10 to the 23rd atoms. So this, if you have 6 moles of carbon or 6 moles of lead, it's exactly the same number of particles, in this case the same number of atoms. So they are equal to each other. All right, in the next one though, it says which one has more mass. So we're looking for more mass, and again we have the same 2 things, 6 moles of carbon, 6 moles of lead. Now they do have the same number of particles, but it doesn't mean that their masses are the same. So if we look at the molar mass of the lead, we see from the periodic table that's 207.20 grams per mole. And if we look at carbon, that one is 12.01 grams per mole. So you can easily see that for every 1 mole of lead, you have way more mass than you would for the carbon. So the answer to this one would be that 6 moles of lead is quite a bit more mass than 6 moles of carbon. All right, the next one we got to decide if the formula shown is an empirical formula, and if so, we're going to put the letter E, or if it's a molecular formula, and if so, we're going to put the M. Now just remember that the empirical is the lowest, simplest ratio possible. Okay, so it's almost the simplified version of the molecular. So we have to look at the formula and decide, is it possible for that one to be simplified any more than it is already. So in the first one we have 2 potassium, 1 sulfur, and 4 oxygen. So this one cannot be simplified any further, so it is definitely the empirical. But in this case it is the actual formula for an ionic compound, because potassium is a +1 and sulfate is a -2. So in this case we have an answer which both would be acceptable, or maybe even having both together would be the actual answer we want. Okay, if we go down to letter B, I have 6 carbon, 12 hydrogen, and 6 oxygen. I could take 6 out of each one of those numbers, so it is not simplified. So then it's the actual formula, which we would call the molecular. On the next one we have another ionic. We have that ammonium with a +1 and a carbonate with a -2 charge. It is in the simplest form possible, so it is the empirical formula, but at the same time, again, is the actual formula for ammonium carbonate. So that would be a molecular formula as well. And then the final one, I can see that they both have 2's, 2 atoms for each one. Could be simplified down, so that one is the molecular formula, not the empirical. Question 8, now we're going to break down into 3 parts here. I didn't think we had enough room to do them all in one slide. So we're looking for the molecular formula for each of these compounds, and each one's been given the empirical formula, and the molar mass is given for that one. So when we say that the molar mass is given, this represents the experimental mass. All right, so we have the empirical, we have that experimental mass. What we have to do is to figure out what is the molar mass of that empirical formula. Okay, so to do that, we list them out like we've done many, many times in this chapter. We have 1 carbon, each one of those has a mass of 12.01. We have 2 hydrogen atoms, each one with a mass of 1.01, so that would be 2.02. And oxygen is 16.00 at 1 atom of those, so that would be 16.00. Grand total, if I add all that up, is going to be 30.03 grams per mole. Okay, So now what we do is we take that experimental molar mass, put that on top of a fraction here, and we will divide it by the molar mass of the empirical formula here. So 120 divided by 30.03. Now we probably don't even have to use our calculator for this one because we're really just looking for the closest whole number. So 120 divided by 30 is approximately 4. And so what we're going to do is use that number as our multiplier and multiply everything in the empirical formula by 4. So it's not just 1 carbon, it will be 4 carbons. Not just 2 of the hydrogens, but 2 times 4 is going to be 8. And then the oxygen would be 1 times 4 as well. So the molecular formula for this one would be C4H8O4. All right, so very quickly, I mean, it's the exact same process here, so I'm not going to spend a lot of time. Here's your experimental molar mass. We've got to find the molar mass of the mercury chloride. I'm not going to work through the problem, but from the periodic table and the number of atoms that I have, the molar mass works out to 236.04 grams per mole. So we're going to divide the experimental from what we found from the molar mass of the empirical. And what I see is I get a number that's pretty close to 2. So it's going to be a multiplier of 2 times. So the actual molecular formula of this one's going to be Hg2Cl2. And there's my final answer in that one. All right, the last one, same exact thing. The molar mass of this one, it works out to be 73.08. And we're going to take that 146 divided by the 73.08, and again it works out to be 2. So my multiplier is 2 this time, so the molecular formula is going to be C6H10O4. Final answer. All right, moving on to a percent composition problem. So in percent composition, we're looking to break down each one of these elements and to find out what percent of the total mass is made up of the mass of each one of these elements. So we have to list them out. We have to count the number of atoms that we have for each one. And hopefully by now that process is a pretty easy process for you. And then we're going to multiply by the number of, from the periodic table of molar mass. So 40.08 for calcium. So that works out to 40.08. Nitrogen is 14.01, so that would be 28.02. And the oxygen is times 16, a little bigger number there, it's going to be 96. Add all of those up, and we get a grand total of 164.10 grams. Now here's the tricky part, it's multiple steps, but we can kind of show it all pretty easily up here in the top. Now we want to take that total mass and divide each of these by that total mass. Now make sure at this point we're not looking at sig figs or anything like that. Molar masses are always going to be carried out to the hundredth place. So don't cut any numbers, don't round any numbers yet here. So 164.10 on each one of these. And then take that answer and multiply by 100 to convert it from a decimal into a percentage. And if we do that, what I see is I'm going to get 24.2%. And I always want to put the units of the substance that I'm in after that percentage sign. So it's 24.2% calcium. The next one is 17.07% nitrogen. And the final one is going to be 0.50% oxygen. And there's my final answer, so we should be circling that whole entire thing right there. Okay, now looking at this, it kind of makes sense. We have 6 oxygens, each of them has a mass of 16, so that mass is 96 grams compared to any of the other ones. That's going to make up the most mass. So just kind of a quick check of the percentages compared to the masses should give you an idea if you're close. All right, so that's how we do those problems. All right, the next one, this is kind of the longer problems for the chapter, those empirical formulas. So you got to remember those steps. Get those memorized in your head. So we're going to go percent to grams, grams to moles, moles divided by the smallest number, and use that to create that empirical formula. Okay, so change simply the percent signs into grams. So we have 57.9 grams of the platinum, and for the chlorine we have 42.1 grams. Now we're in grams, convert the grams to moles. So we're going to use that molar mass of 1 mole on top for each one of those. And then from the periodic table we're going to list out their molar masses. So 195.08 grams of the PT, and on chlorine that one is 35.45 grams. Calculate that out on your calculator and I get 0.297 moles of platinum, and on the bottom one 1.19 moles of oxygen. Now again, we're kind of in an intermediate step here, so you don't want to be cutting this off to exactly 1 or going all the way to the 10th place. So you should carry that out at least to the hundredths, if not to the thousandths place there for this kind of intermediate step. Alright, now we're going to find the smallest of the two, so 2.297 is going to be the smallest one, and we're going to divide each of them by that 0.297. And when I do that, I definitely is going to get one of the answers to be a 1, and that's this one. So we have one of those, and then when I divide this out, what I end up getting is a number of 4.01. So very close to 4 and close enough for us. So now from these numbers, I'm going to create that chemical formula. So it's going to be PT, and I have one of those, followed by chlorine, and I have 4 of those. So PtCl4. Now when it says give its name, now I just want to name this compound. So it's going to be platinum chloride. Now the tricky part on this one is platinum has multiple oxidation numbers, so I need a Roman numeral in there. Chlorine being a -1, and I have 4, the total negatives is -4. I have 1 platinum here because there's no number there, so it must be the +4 oxidation number. So it's going to be platinum Roman numeral 4 chloride. Alright, very similar problem, so we'll kind of go through this one probably a little quicker here. Again, looking for that empirical formula, and I've got it in percentages. Now the only difference is this is a little bit bigger problem because we have 4 substances in this compound. So list them all out. Start with the top one. Sodium 28.05. Change the percentages right into grams. Next one is going to be 29.26 grams of carbon, 3.66 grams of the hydrogen, and 39.02 grams of the oxygen. Convert each one of those into moles by using the molar mass, which is 1 mole for each one. Oops. And 1 mole of the oxygen. And for each one, put in their molar masses from the periodic table. Okay, sorry about the mess here, it's a little tight, but I think you can probably figure it out, especially if you've already worked out the problem. So, alright, when we calculate this out, in the first one, what I end up getting is 1.22 moles of the sodium. I get 2.44 moles of the carbon. I get 3.62 moles of the hydrogen. And the final one, 2.44 moles of oxygen. So I went from percent to grams, grams to moles. Now moles divide by the smallest number. So looking at this, I see that 1.22 is my smallest number, so I'm going to divide each one by that number. And most often you can probably do this step in your head as far as calculating, because we're looking again for that nearest whole number that we get when we divide. So 1.22 divided by 1.22, obviously 1. This one looks like it's going to work out to be 2. This one very, very close to being 3. And the last one is going to be 2 as well. So from this, I can see that my empirical would be 1 sodium. It's going to be 2 carbons, 3 hydrogens, and 2 oxygens. Now as far as naming this compound, we've got a metal first, so it's going to be sodium. followed by a polyatomic that looks like C2H3O2 and is called acetate. So this is a two-parter. We've got two answers. Let's circle them both so we can see that final answer. Now, just a reminder that when we're taking the test, we need to see all of this work here. We cannot be skipping steps, doing some of the steps in our head. We've got to show it all so we can get all those points for that. All right, and the final one. In this one, we're actually looking for the molecular formula. Okay, so this is an extra step here. We do have those percentages again, and we also have this experimental value for molar mass. Let's put molar mass there. Okay, so if we're trying to find that molecular formula and we're given percentages like we've got in this problem, basically it's an empirical formula problem first. So do the same exact steps that we did in just the last couple problems there. So we're going to take the percentages, change them to grams, 76.54 grams of carbon, 12.13 grams of hydrogen, and 11.33 grams of the oxygen. We're going to change those from grams into moles. 1 mole up on top, molar mass on the bottom. And we will get our calculator to do the next step for us. We get 6.37 moles of carbon. The next one I get 12.01 moles of hydrogen. And the final one is 0.708 moles of oxygen. Okay, so we've gone grams to moles. Now moles divided by the smallest number. So I see that the bottom one here, 0.708, is my smallest. So each of them gets divided by that number. And so what I get at this point is going to be, obviously this is going to be my 1, but this one works out to be about 8.997 something. So really that's a 9. And this one works out to 16.96, so that one is a 17. So take those numbers and create that empirical formula. So it's going to be C9, H17, and 1 oxygen. Okay, so this is my empirical formula here, but this is not my final step. But it would be a good thing to kind of just label that as the empirical so that we can see that. Okay. Now, the next step is to find the molar mass of this. So now what we have to do is take and list out each of the elements. And I know this is a lot of steps, but this is what was required. And again, on the test, you have to show this step if you're going to get any of your points for that work. All right, so we have 1 of those at 16, 17 of those at 1.01, and carbon, 9 of those at 12.01. So 108.09, 17.17, and the last one would be 16. So the grand total of the molar mass is going to be 141.26 grams per mole. Okay, so this is the molar mass of the empirical. Compare that to the molar mass that was found experimentally for you. So take this 282 as your top number again, divided by your 141.26. So when you divide that out, again, we're looking for some whole number here. So 282, 141, basically the number is 2. So your multiplier is going to be 2 times whatever the empirical formula was. So instead of C9, it's going to be C18, H34, and oxygen is 2. This is your final answer. But I need to see all of these steps in between to give you full credit for the whole thing. All right, we have one final problem here, and that one is on hydrates. So in the first one, we're just naming that hydrate. So focus first on that first part, which is an ionic compound. Break it into 2 parts. The first part is strontium, and that is followed up by the element chlorine, so we say chloride. And the last part, we focus on the water part of it, pay close attention to the number of molecules that we have of that. So it's 6, and for 6 we say hexa, and for the water part we say hydrate. So strontium chloride hexahydrate is the name. Now the percentage of water is very similar to the percent composition that we've done before. It's a little special because again we want to treat the water differently. We're looking for how much mass all of those water molecules make up out of the whole. So list out your elements: strontium, chlorine, hydrogen, and oxygen. Kind of break this into two parts here. Strontium, you have one of those at a mass of 87.62. The chlorine, we have two of those, each one being 35.45. So that'd be 70.9. Now the hydrogens, we have 6 molecules, so it's going to be 6 times 2 is 12. So 12 of them each at 1.01. And the last one, we have 1 oxygen here, but 6 molecules of the water, so it's going to be 6 total oxygens, each at 16 for a grand total of 96. Now when we total this up, we actually want 2 totals. We want the total of all of it, the whole entire substance, and that would be equal to 266.64 grams. And then I want the total of the water molecules themselves, and that would be 108.12. Now, just like we did in the percent composition, take the part that we're interested in, 108.12, and divide it by the whole thing, 266.64. Then take that number, whatever you get, times 100, and always carry this one out to the hundredths place. So it's going to be 40.55%, followed by the substance that I'm looking at, which is water. Circle your final answer. All right, hopefully this video was helpful to you, and if you still have any questions, make sure that you ask your teacher. All right.